Bless your heart. Some kind of way you done found yourself for the online tutoring of Mr. Whittington's. Is it Mr. or Mr.? Mr. Whit? How that man say that? Anyway, today's episode is on factories. Now I don't know what in this Sam here any of this mean, but I hope you enjoy yourself, so get your ink pen and your pencil and get ready to learn about factories.
Ladies and gentlemen, this is Mr. Whit with Fort Bend Tutoring, and today we have a wonderful tutorial for you, and it is going to cover factoring with complex numbers. That's right, we'll have imaginary numbers involved in our factoring process. I know you can't wait because I cannot wait. But first and foremost, I'll ask that you subscribe to our YouTube channel, Fort Bend Tutoring, FBT, where personalized tutoring is the solution. Go ahead and subscribe. Click on that icon on your screen to subscribe to the YouTube channel, and of course click that bell icon so that you can get notified when we upload new and fresh content, whether it be live or studio like this video. Now that we have that out of the way, let me go ahead and give you guys a snapshot of the 8 problems that I have for you in this video. Here they are in all of their glory. That's right, we have problems numbers 1 through 8, and we will be factoring with the imaginary numbers, those complex numbers. Amen, amen. I know you can't wait because I can't. Let's go ahead and get a quick refresher over the imaginary numbers. Now, of course, we already have uploaded an imaginary numbers and complex numbers video, so go ahead and check that out. I'll make sure that there is a link on your screen there so that you can check out that free video from Fort Bend Tutoring that covers imaginary numbers. And within that video, you'll find that the imaginary number I is equivalent to the square root of -1. Normally an undefined value. It's been defined with this imaginary number I, and there's a sequence that goes along with that. In other words, if you have I to the first power, it equals to I, but more importantly to us and in this video, that I squared is equal to -1. So you want to definitely keep this one in mind right here within that sequence, that I squared is equivalent to -1. And we also have a sum of squares video where we're factoring a sum of squares, and normally that would be prime. In other words, it cannot be factored any further, but with the help of our imaginary numbers here, we can factor it using this factoring pattern that you see right here on your screen. So we'll be using all of this information in this video as we go through numbers 1 through 8. That's right, me and you right now getting down with some complex numbers, and of course my favorite thing to do in math, factoring. Let's go ahead and get this video underway with problem number 1. Here we have 9a squared plus 49. Now, normally you should recognize this as a sum of squares. Oh yes, you should. However, because this video, and it's an AP video, that's right, AP much, we're going to be factoring this expression, this quadratic expression. We're going to be factoring this expression using that aforementioned factoring pattern for a sum of squares. As I approach factoring this problem, I'm going to go ahead and show you guys every single step that I'll do in order to factor this sum of squares here. We know that the first term is 9a squared. That's a perfect square. We know that the second term is a perfect square. That's 7 squared. Of course, we have a plus sign in the middle, so that is a sum of squares. However, if I do some substitutions here and show that I can rewrite this expression as 9a squared minus -1 times 49, we can go ahead and then take our next step and show that this is 9a squared minus 49i squared. So noticing that I know that the opposite of a negative is a positive, which would give me back the original expression, we can go ahead and replace this -1 with I squared. Remember, we said the value of I squared was going to be equivalent to -1. So that's where I'm showing my substitution in my process. Since I was able to rewrite this sum of squares as now a difference of squares, we can go ahead and use our difference of squares factoring pattern and open up 2 sets of parentheses. And because I'm an optimist, I'm going to rewrite this first binomial as 3a plus 7i. Then I'll be multiplying times the binomial 3a minus 7i. And of course, please check out our difference of squares video if you want to get more familiar with that factoring pattern for a difference of squares. And it's at this point that we're done. That's right, it's over. Yeah, it's over here. Just let that sink into your soul that we are done. But of course, because we're FBT, we're going to be red boxing our answer. That's right. Check me out with a red box containing the answer within. That's right. It's over. Seeing everybody walking by, I can see that this answer is done because I've clearly put a red box around it, as you should with your answers, because you want to show off your correct answer to your teacher and your classmates. So let's come along. Follow me. So here we have problem number 2, and we have the expression x squared minus 7ix minus 12. Well, the problem is already showing its hand in a way because they're letting you know that there are imaginary numbers used to create this expression. And what do we mean by that? Well, knowing that I squared is equivalent to -1, we can rewrite the expression showing that it is x squared minus 7ix plus -1 times 12. Now, why is it important to rewrite it this way? Because now I can show that this expression can be rewritten as x squared minus 7ix plus 12i squared. So that was the purpose of showing this step right here, that I can go ahead and use my substitution for -1 in the form of I squared, which gives me the capability of clearly seeing as to how this I is going to be utilized in the factoring of this expression here. So that means I'm going to now open up 2 sets of parentheses like so. I know that the first term in each binomial is going to be my variable x, and I'm going to focus on the fact that I am going to be looking for 2 factors of 12 that will add to give me 7. So knowing that the factors of 12 are going to be 1 times 12 and 2 times 6, and we also have 3 times 4, the 2 factors that will multiply to give me 12 and add to give me 7 are going to be 3 and 4. But in this case, I'll need these second terms in each binomial to be represented as 4i and 3i, with both of those values being the sign of the middle term's coefficient, which is negative. And this is our factorization for this problem. Now, I'm going to go ahead and put a red box around this because I know that this is the answer here, but I'm going to prove to you as to why this answer will work. And you can prove every result that you find in this video by multiplying your result out. That's right. Go ahead and get your arrows popping and multiply your result out using the distributive property or the FOIL method. There you go. So what we'll be doing is multiplying this out, seeing what our answer is, confirming, verifying that our answer is the original expression. So multiplying x times x, we'll get x squared. Multiplying x times -3i gives me -3ix. Then multiplying -4i times x, that gives me -4ix. Then multiplying -4i times -3i will give me a result of positive 12i squared. Oh yeah. Then combining our like terms, we'll have x squared, the -3ix, and the -4ix combined to give me -7ix, which looks familiar, right? And of course, we should realize that the I squared is equivalent to -1. Now that we have this, go ahead and multiply that 12 and -1 together, and you'll confirm that your result is the original expression because I have x squared minus 7ix minus 12, and that checks out with the original expression. And there you go. That's right. See how we did that? Done and done. That was problem number 2. Let's move on. All right, here we have another problem. This is problem number 3. We have 4x squared minus 8ix minus 3. And of course, I want to once again show that we have imaginary numbers embedded within this expression. So I'm going to rewrite this as 4x squared minus 8ix plus 3i squared. So notice how I took that negative and went ahead and wrote it as I squared in this situation. We will then go ahead and factor this by looking first for our master product here. What do I mean by that? I'm referring to our factoring quadratic trinomials part 2 video, where I'm asking you to multiply the first and the last digits together. In other words, the a and the c value, multiply that together to get 12. So once again, we're looking for 2 factors of 12 that will, in this case, add to give me 8. So to remind you, our factors of 12 are going to be 1 times 12, 2 times 6, and 3 times 4. And we need 2 of these factors that multiply to give us 12 to add to give you 8. Well, we know that the 2 and the 6 will do just that. So I know that I will start out with my variable as the first term in the binomial. I'm going to also use 6i and 2i. Remember, we need an I and an I in that second term in order to give us that I squared that we'll need. Then, as far as the sign on the 6 is concerned, the sign of your middle term will always be the sign of the largest factor. So because our middle term's value is negative, then the 6 needs to also be negative. And since we're adding to get the -8, well, they both need to be a negative, all right? So remember that like signs add and unlike signs will subtract. So we needed these two values to add to give us -8, and -6i and -2i will do just that. Well, because we had a leading coefficient of 4, which is not 1 as we saw in the previous problem, I'll be dividing both of these values by the leading coefficient of 4. From here, I'll be simplifying my results, so I'll end up with x minus 3/2 I times x minus 1/2 I. And then any remaining denominators will be placed in front of their respective variables, okay? So I'm going to be moving these denominators in front of the variables, and I'll end up with 2x minus 3i times 2x minus I, just like this. And this is the answer to our problem. Ladies and gentlemen, we're going to red box it. All right. And of course, you can always multiply your result back together to confirm that it gives you your original expression. Amen. Amen. And that is problem number 3, guys. Let's move on to our next example. We have problem number 4, and in problem number 4, not only do we have imaginary numbers, but we also have radicals involved. That's right, square roots. So if you missed our factoring with radicals video, go ahead and check that video out. Of course, I have a link right here on your screen. Matter of fact, it should be about right there. There you go. It should be right over there. Okay. There should be a link for you to check out that video that involves factoring with radicals. I would love for you to check that video out. So here, let's go ahead and do some rewriting here, because we want to show not only that we have the imaginary numbers embedded in this expression, we also have the square root of 5 embedded as well. So let's go ahead and do some rewriting here. Let's start by showing that this is going to be x squared minus 2ix times the square root of 5. And this is going to be minus 15i squared, just like that. All right. In addition to this, we need to make sure that we're focusing on the fact that we will have that 5 already taken care of times 3. So because we have this 5 embedded here, that's going to take care of that square root of 5, because we know that a square root of 5 times the square root of 5 will give us this 5. So we need to focus on the 3 as far as our factors are concerned. So the only factors of 3 are going to be 1 times 3. So once again, what happened was I was able to take out a -1 from this positive 15, rewrite that as I squared, and because we already have this square root of 5 in that middle term there, I know that they're going to eventually square that square root of 5 to give me this 5 here. So I don't need to be concerned too much about the 5 when I factor this quadratic expression. What I do need to be concerned with is factors of 3. Yeah, that I need to be concerned with. So that's why we're looking for 2 factors of 3 that will subtract to give me 2. And of course, that's just going to be the 1 and the 3. So you heard me say all this. How is all of this going to play out is more important to you, right? So how do I set it up? Well, for starters, just start with your variable x. And as far as the second term in each binomial is concerned, you'll need a 3i times the square root of 5, and you'll also need an I times the square root of 5. Okay, and then the sign of the 3 needs to be the sign of this middle term's coefficient, so that needs to be a negative, and the sign of the second term in the second binomial here needs to be positive, because we need these two coefficients, that -3, that +1. We need those coefficients to subtract to give us -2. Okay, and that's how that'll play out. From here, well, all we need to do is put a red box around it, because it's over. Yeah, you thought that there was still more to do, but it's over. Okay? Yeah, it's over. Here, let me prove this to you. So going ahead and getting our arrows popping. Okay, let's go ahead and prove this works. We have x times x, which gives us x squared. We have x times I square root of 5, which gives you I x square root of 5. All right, let's just write it that way for now. Then we'll have negative 3i times the square root of 5 times x. That'll give you a negative 3i x square root of 5. And then finally, when multiplying a negative 3i square root of 5 times a positive I square root of 5, you'll end up with a negative 3i squared times 5. Okay, and of course we get the 5 from multiplying square root of 5 times square root of 5, which is technically square root of 25, which reduces to 5. Okay, then we'll go ahead and combine our like terms and multiply that last term there. So combining ix square root of 5 and negative 3ix square root of 5, you'll end up with negative 2ix square root of 5. And then we'll have negative 15 times negative 1, because the I squared is equivalent to negative 1. And of course, negative 3 times 5 gives us negative 15. Continuing to simplify, you'll have x squared minus 2ix times the square root of 5 plus 15. And this verifies that our factorization of the original expression is spot on. That's right. It works. It just does. Yeah, that was problem number 4, guys. All right, let's check out the next problem. Problem number 5, we have 6x squared plus ix plus 1. We want to first of all rewrite this, showing that there is an embedded I squared term within this problem. We know there is. So next we'll be multiplying the first coefficient and the last coefficient to give us 6 as that master product to be concerned with. So factors of 6 are going to give us 1 times 6 and 2 times 3 for options here. We're looking for 2 factors of 6 that will subtract to give us 1. Well, that's going to be 2 and 3, right? So that means I'll be opening up 2 sets of parentheses here. I know I'll need my variable x. I know I will be needing 3i and 2i. Okay. And if you haven't noticed, I like to lead with that largest factor. Okay. So out of the 2 and the 3, I put the 3 first because it's the bigger number. And with that, I'm able to always identify the sign of that largest factor because it will always be the sign of the middle term's coefficient. Because we're subtracting to get that middle term's coefficient of 1, I know that 2 needs to be negative. Okay, so that's how I always have a clear vision of what my signs need to be on the factors that I find. Because I have a leading coefficient of 6 in the original problem, I'll be going back and dividing each of these factors by 6. Now I'll be simplifying this. I have x plus 1/2 I times x minus 1/3 I, and then any remaining denominators will go in front of the variables. Okay, so that means that my answer here is going to be 2x plus I times 3x minus I, and this is the answer. Red box it. Got a red box around my answer. Amen, amen. And that was problem number 5, guys. Let's move along. So here we have problem number 6 with 12x squared minus 7ix plus 10. So I'll be starting out by rewriting this problem as 12x squared minus 7ix minus 10 I squared. Once again, I know that there's an I squared in play because we have that middle term with that I involved. All right. And the third term doesn't even have an imaginary number in it. So I know it took an I squared to give me an integral last term's coefficient. So that means that I'll be looking for factors of the product from 12 times 10 that'll subtract to give me 7. Well, this number is going to go over 100. So if you checked out my factoring quadratic trinomials part 3 video, you know I don't like to have that master product go over 100, right? So let's use some prime factorizations of those coefficients here. So 12 is equivalent to 2 times 2 times 3, right? And 10 is equivalent to 2 times 5. All right. So what if we were to put all of those 2's together? Well, we know that 2 times 2 times 2 is 8, right? Okay. And then what remains is 3 times 5, which is 15. Well, doesn't 8 and 15 subtract to give me 7? It does. That means that I can use this to factor this expression. All right. So we're going to start out with x as our first term. Okay, in each set of our parentheses, and I'll be using 15i as well as 8i. Okay, and then I also know that I'll need to have the 15i be negative. Why? Because it's the sign of the middle term's coefficient. That's why. Then the 8 needs to be positive. Why does the 8 need to be positive? Because we're subtracting. This last term's coefficient tells me that we need to subtract the coefficients to get that middle term, negative 7ix there. From here, because we had a leading coefficient of 12, we'll be dividing both of these values here by 12 and then simplifying. From here, we'll be simplifying these values. So we end up with x minus, and simplifying the 15 and the 12 by 3, we'll have 5/4 I, and then we can reduce the 8 and the 12 by 4. That gives us 2/3 I, and then any remaining denominators will go in front of the variables, okay? So you'll end up with 4x minus 5i times 3x plus 2i, and red box it. That's right. This is your answer, ladies and gentlemen. Done and done for problem number 6. All right. And remember, you can always multiply your result out to verify that your result is equivalent to the original expression. All right. That's problem number 6. Let's move on to problem number 7. Here we have 3x squared plus 7. Well, yeah, we're going to treat this like a sum of squares. You know, how do I know that? Because using radicals in this problem, as well as using imaginary numbers, we're going to say that we're looking at 3x squared minus 7i squared. All right. So we're going to keep in mind that I squared is equivalent to -1, right? So the opposite of -7 is going to be +7. That's why we're able to do that. So using our difference of squares factoring pattern, I'm going to open up 2 sets of parentheses, give myself a little room in this one. We'll write our first term, the square root of 3x squared, as x times the square root of 3. And then for the second term, we'll be writing that as I times the square root of 7. And because I'm using the difference of squares factoring pattern, I always like to lead with a positive first because I'm a positive person, and then follow up with the negativity. There you go. And we're done. Yeah, I already know that you don't believe me. That's why I'm going to multiply this one out for you. Notice I already put my red box around the answer because it is the answer. I'm going to get my arrows popping over here, guys, as I prove to you that my solution is correct. We have x times the square root of 3 times x times the square root of 3. That's going to give me 3x squared. Oh, yes, it will. Then I'll be multiplying x times the square root of 3 times -I square root of 7. That gives me negative ix square root of 21. How you like that? Then multiplying I times the square root of 7 times x times the square root of 3, that gives me a positive ix times the square root of 21. And then finally we have I times the square root of 7 times a negative I times the square root of 7. This gives us a negative I squared times 7. See, what happens with our middle terms here is that they're going to cancel out, right? And then we know that we have a negative 1 times 7. Well, that's just going to give you 3x squared plus 7 as a result, which will confirm that our factorization is accurate. That's right. It's correct. In other words, it's the answer. Done and done for problem number 7. Are you having fun yet? Because I am. Let's move on to our last problem, problem number 8. Problem number 8 is here. Oh, yes, it is. And let's go ahead and show that we can rewrite this. So I'm going to start by showing that this is 4x squared minus 27i squared. However, we may need to use some radicals in this. So if I'm going to use a radical in this, I may want to show that I can write this as 4x squared minus 9 times 3i squared. Now, I wrote it this way because I wanted to show you guys how I was going to end up with a radical in this problem. See, we already know that 4x squared is a perfect square. We already know that 9i squared is a perfect square. But this random 3 that's left over, it's not a perfect square. So we're going to need to use radicals to assist us in this problem. So we're going to start by opening up 2 nice large sets of parentheses here. And the square root of the first term is going to give us 2x. The square root of the second term is going to be 3i times the square root of 3. Doesn't that look juicy? So what happens here is, because we're doing the difference of squares factoring pattern, I like to lead with a positive and then a negative. That's right. Push all those bad thoughts to the back where they belong. And then from here, we're done. Yeah, I'm going to put a red box around this. Red boxing it. Yeah, is the answer. Oh, ye of little faith. Let us go ahead and multiply this out for you, because I can sense the doubt. I can sense the doubt. You're like, Mr. Witt, I know I've seen it already multiple times from you, but I still don't see how this is going to work out. Well, let's see. We'll have the 2x times 2x. That gives us 4x squared. Then we'll have 2x times negative 3i times the square root of 3. That gives you negative 6ix times the square root of 3. Then multiplying 3i times the square root of 3 times 2x, you end up with a positive 6ix times the square root of 3. Then multiplying 3i times the square root of 3 times negative 3i times the square root of 3, you'll end up with a negative 9i squared times 3. Just like that. We know that our middle terms are going to cancel out here. They're gone. Goodbye. And we have 4x squared minus 9 times negative 1 times 3, which equals 4x squared plus 27. And this verifies that our result is correct. Amen, amen. So what you need to remember, ladies and gentlemen, is that you can factor a sum of squares using complex numbers. That's the first thing. And then, of course, if you already see a middle term in an expression that has an I there, especially when you're dealing with a quadratic trinomial, then you should know that you'll need to use complex numbers when factoring it out. All right. And we hope that you will go ahead and rate, comment, and subscribe. Of course, subscribe to Fort Bend Tutoring's YouTube channel. This is me, Mr. Witt, and Fort Bend Tutoring, saying peace.
FACTORING. This includes topics such as GCF, that's the greatest common factor, like Obama, the difference of squares, quadratic trigonometry. Oh Lord, that's when the pig is sick on all four sides. The sum of cubes. That sounds like one of them games they play. Difference of cubes. Oh, that's just ignorant. AC method. Yes, honey, because you got to have your air conditioning in Texas. And factoring by grouping.
Thanks for watching. We appreciate you hanging out with Fort Bend Tutoring. Like the video, comment, and subscribe. Hit up our website, tutoringmath.net, and set up a private tutorial with me and FBT. Oh yeah, baby.